Hello, thank you for joining me today. What I'd like to talk about today is probably one of the most encouraging trends I have seen in terms of a future for our industry in quite some time. I'm going to talk about digitalization. Now, it's a relatively inelegant word, but it's a representation of what we see as a fundamental change of the business landscape, whether it be aspects of putting in place increasingly smart systems capable of being reconfigured on the fly, capable of delivering new and unprecedented user experiences, or talking about how companies are digitalizing their whole business operations, where not only being able to do design simulation, but increasingly moving more and more of their business fabric onto a semiconductor framework, enabling them to do things like move from a on-site premise type of work environment to one where they have their employees distributed around the globe, as we've been forced to do during the pandemic. You can start to see some of these trends when you go look out in the market what's happening. So here what we can see is a chart that shows the capture of electronics revenue being done by semiconductor. Historically, from about the mid-90s on, this was at a fairly constant level of about 16% of overall electronics being captured by semiconductor. But as we increasingly put out new smart systems that have greater abilities overall, we're seeing that move to where by the time we hit 2026, we're looking at 25% of that content being driven off a semiconductor. So that's a significant increase and a real opportunity for the companies in the industry. You can also see the importance of semi to the systems houses by the fact that increasingly the systems houses are becoming IC design companies as well. Certainly the first part of that trend was done in areas like the smartphone, where whether it was Apple, Google, or others, increasingly companies in that space went off and started doing their own design. But you're seeing it happen in other areas as well, whether it be in communication space or things like automotive, where the OEMs and tier ones are increasingly becoming designers rather than consumers of semiconductors. And this isn't just a matter of there being a couple of press releases and an occasional chip being announced. This chart shows the percentage of the foundry customer revenue being driven off of traditional fabless companies, traditional IDM companies, and these new systems companies. And what you can see is whereas a decade ago, the systems companies were a trivial part of the foundry revenue, that has increased to where now it is forecasted to be at about 21.3% next year, which represents a compounded annual growth rate of almost 27%, which is significantly higher than the other two spaces. Now, clearly, a lot of that has been in the areas like Apple's iPhone, but this is increasingly becoming more and more of a trend as these systems companies attempt to take more control over the architecture and be able to deliver, hopefully, a better experience for their customers in their overall application stack. Now, if you look at this moving forward, we really see four trends that are driving this potential for these companies to go off and accomplish the goals they have for their digitalization strategies. First off, sensors. The ability to digitalize the natural world and bring that into a compute infrastructure so that you can put out new types of applications. Edge compute, which increasingly through our ability to integrate more devices into smaller footprints and apply things like machine learning and AI within those chips, we can do more and effective compute at the edge. 5G provides us an infrastructure that enables us to pull these devices together, and the cloud and data center allows us to then take this final set of data and deliver those end applications to the customer. Obviously, all of this is being enabled as well by a pervasive AI environment that allows us to be effective on a watt per compute scale in terms of being able to pull this together. Take a look at some of the data that is then being driven off of these trends. When we first started pulling this presentation together, one of the theses was that indeed sensor data was becoming an important driver of this, and the number of sensors were increasing. Little did we know when we pulled the data how much of an increase that has been. Here you can see a chart starting in 2015 versus 2025, and this is a count of sensors connected to the internet. And what you can see here is in 2015, there were about 1.6 billion. In 2025, that's expected to be almost 30 billion sensors, which is a 34% CAGR during that term. This is an explosion well beyond anything we had thought we were going to be seeing. And keep in mind, again, that this is not just sensors alone. Those sensors will increasingly be producing more and more data. That data needs to be processed at the edge. It needs to be communicated, and it needs to be aggregated at the data center. So you can see the beginning of this explosion of opportunity down through that chain. Here we'll take a look at 5G. Certainly 5G in its traditional space for the infrastructure and your wireless space for communications, it is a strong growth opportunity expected to grow at about an 18% rate over the next few years. But what you can also see is that application of 5G to those IoT types of spaces, whether it be consumer, automotive, industrial, that is going to be an even larger driver of this opportunity as, again, people start to try to connect those sensors together and move that data up into the data center. Data centers themselves, you can also see a fairly significant increase in growth and opportunity there, which I think explains a lot of the battle that's occurring right now to become that main architectural source for compute in a data center, whether it be based upon GPUs or CPUs. And the way you can see that there is that having driven a strong recovery from the dip in 19, in many ways based upon the whole aspect of moving to a virtualized work environment because of the pandemic, casting forward over the next 5 or 6 years, predictions are for an 11% CAGR in that very large market, driving towards a 14% CAGR in the out years leading up to the end of the decade. And we talked about how AI is a pervasive technology that will be infused across that entire compute chain. You can see that when you start to take a look at some of the data in terms of what it's looking like for semiconductor growth moving forward. The chart on the left shows overall semiconductor, and indeed you're reading correctly. Predictions seem to be lining up these days for a $1 trillion semiconductor market in about the year 2030. But if you look at the details there, what you can see is there's this pretty significant difference between baseline semiconductors versus semiconductors that have AI functionality. And what you can see is whereas somewhere around this time frame, about 10% of the chips that are being produced have some sort of AI on them. Notable examples being things like those cell phone application processors that have AI engines to do things like facial recognition. That moves to where about half of the market will be represented by chips with AI context by the time we hit the 2030 timeframe. Now, I'd like to step back for a second on something I think has been really interesting over the last few years. I joined the semiconductor industry in the early 80s. And certainly at that point in time, it was an industry with an awful lot of swagger, an excitement about what we were doing, a sense that the possibilities in the future were unlimited. That really started to change right around 2000. Coincident with the dot-com crash, you started to hear a whole lot more about things like, I believe that was the first time I saw an article that said Moore's Law is dead. You started to see more about things of growth had gone out of the industry, that we needed to do consolidation rather than new company formation strategies. And in general, we just lost an awful lot of swagger. Well, I think you can see part of the reason behind that when you compare our growth rate versus what the overall economic growth rate has been. In the 80s and 90s, semi was growing much stronger than the overall economy. Now, those of you who were there realize that there probably, in that decade where we had a CAGR of 14.6, there was probably not a single year where that was actually our growth rate. We always have been a bit subject to the boom and bust cycle. But overall, we were growing much stronger. 2000s, we were almost flat during that decade versus GDP growth at about 6% globally. 2010, there was some recovery, but we were still lower than GDP growth. Well, the good news is when you look at now these trend lines moving forward, when you look at the fact that we are becoming so much more fundamental, not just to compute and devices, but to fundamentals about the company's existence globally, we're expecting now a growth rate where, again, we will be ahead of GDP growth rate moving forward. And I think that leads to a lot of what you're about to see in the next few slides, which is this aspect of how investment is increasing. The first thing to look at is VC investing. Previously, we were running at about $2.5 billion a year, rolling up into the dot-com crash. The dot-com crash dropped that down by about 40%. We ran for about a decade, $1.7 billion. 2009, the Great Recession, dropped that down to where we were under $1 billion a year average being spent on semiconductor content. And this was certainly the time where everyone said there was going to be consolidation in the industry. Continued to fall off up through 2013, where it dropped down to $500 million. This was at the point where many articles talking about how the age of investing in large chip companies was done and that the only opportunities were for things like IP or small chip analog. Well, you can see that trend has flipped, and it's flipped in a major way. Moving from previously where a $2.5 billion year was a good year, you saw in 2021 we almost had $10 billion of investment flowing into startup companies in the semiconductor space. And this is a trend line that has also expanded globally. Previously, the vast majority of spending was being done in the U.S. You can see here now the U.S. has had a very strong 2021. A year that, in fact, more investment in the U.S. than there was in the entire industry previous years, but that spending is now gone global. China, with their well-known effort to become a more important provider in the semiconductor space, led with almost $6.5 billion of spending. But even the rest of the world outside of U.S. and China, you saw about $1.6 billion of investment driving into those companies. So this is a global trend. And I think you're going to see this trend continue to increase as more and more nations are realizing how strategically important semiconductors are for enabling their overall economic growth. You can also see this investment flowing through into the foundry space. So here what we're looking at is the distribution of advanced logic for capital expenditures in the foundry space. You can see here again, relatively flat spending from the years up until about 2018. 2019, we started to see an increase in that spending. We hit almost $80 billion in FY21, and we've already seen the announcement from one single customer, TSMC, who has come out with saying that they will spend approximately $40 billion on enabling new foundry capacity next year. So we can expect to see overall this number will probably increase again significantly in overall spend. And I think this is again another trend that we can rely upon moving forward. Things like the supply chain crisis indicate a pretty significant gap between capacity and demand at this point in time. And the whole aspect of nation states becoming far more concerned about their ability to keep access to semiconductor technology will probably drive this trend again, one that will increase and diversify globally. You can also somewhat see this trend within the R&D spend within the established companies. Now, to date, we have numbers up to about 2020. Through that period of time, we're approximately flat in terms of percentage of revenue. Obviously, revenues have been increasing significantly, so that does indicate more investment. But this does bring up a fundamental question of, with the presence of so much money going into the startup companies, with the space of the opportunity that we're looking at in the beginning, I think it's a viable question that companies should be asking themselves, are they investing sufficiently against those opportunities moving forward? I think another interesting way to look at investment is to try to take a view into what's happening in terms of design activity within the country. And if we take a look over the last 10 years, globally the EDA industry revenue has been growing at about 9% CAGR. But in Korea, it's been growing at 12%, which is an indication that increasingly more of the design activity is being done in Korea, which provides a good foundation for this industry here locally moving forward. And so we've talked about how this digitalization is changing the overall economic landscape, how semiconductors are becoming a more critical part of implementing not just your normal electronics, but whole companies' infrastructure and how they present themselves to the world. We've seen that that is now generating a level of investment and an opportunity that is worthy of that investment. And what I'd like to talk about next is what we're doing in terms of the EDA industry to help enable this. Three main pillars. First off is technology scaling. As I'll discuss in more detail, we still see one of the fundamental benefits of people implementing this digitalization is the fact that we can continue with Moore's Law, scale technology, and deliver more functionality at the same cost over time, which enables them to transform themselves and have a very positive future. Secondly is design scaling. Moore's Law does have a dark side. I can produce twice as many transistors on a die every 2 years. I have to design twice as many transistors every 2 years. And we need to put in place new methodologies that enable us to do so without having to have an exponential increase and explosion in cost continuing that would eventually make it very difficult to justify an NRE cost against the amount of chips that we expect to have to produce for the globe. And then finally, there's this aspect of system scaling. Increasingly, that environment I talked about where you have a sensor driving into some edge compute that would work through 5G to the data center is that the application needs to get validated across your semiconductors before you produce them to ensure that overall the application can fit within the parameters it has and the user experiences that it's expected to deliver. Underlying all of these is the need to do that same pervasive AI enablement that's happening in the application market is also going to occur within the EDA tools, and to be able to deliver that on a cloud infrastructure that enables a flexible compute environment where my data center is not my constraint on my design activity. So first off, let's talk about technology scaling. I have been amazed at how consistent it has been for almost 2 decades now for declarative statements saying Moore's Law is dead. And so I've been collecting this chart now for about 5 or 6 years. And it's all public information. And the good part about Apple having become a chip producer is that people really stare at this chip. And so you can pull data consistently upon what they've been able to deliver over time. So what you're looking at here is an 8-year time horizon. So that's 4 Moore's Law cycles. Doubling every cycle means 2 to the 4th, which would mean 16. If you look here, the 2013 A7 processor had approximately 1 billion transistors. The 2021 A15 had approximately 15 billion transistors, almost exactly on that schedule that you would expect from Moore's Law. And it hasn't just been density. It's also been performance. Now, the one thing I will say is I clearly do not believe Moore's Law is dead, nor do I believe it's dead moving forward. But things like Dennard scaling did die, where the ability to get increasing performance just by dint of shrinking the features of the design went away. But even if you look at performance of these chips, it's amazing the story. The A7 on a Geekbench single CPU score, 269. Coming forward into the A15, 1734. An incredible increase, and that increase is mapped against multi-core performance. It's mapped against GPU performance as well. Now, much of it has been architecture. Much of this has been design technology co-optimization. But this is why digitalization is so important moving forward. That ability to move on to this cycle in terms of what you can deliver from your company is critical to the survival of well more than just electronics companies and why you see that macro trend occurring so much. Now, clearly, it won't just be Moore's Law. Increasingly, what we're looking at are packages that are multi-heterogeneous dies, things that, whether they're called 3D, 2.5D, what some people have called more than more. And here what becomes important is an aspect of supporting system technology co-optimization, to be able to look at the overall architecture of the package and be able to apportion that into different elements, potentially in heterogeneous technologies, using a different technology process, for example, for an RF portion versus using for a logic portion. Understanding what that'll mean in terms of overall performance, driving that build out of the overall architecture, pushing that forward into what its overall floor plan will be, how that'll manage performance. This is going to be an important new cockpit moving forward and an area we expect to see significant investment from the EDA industry. Now let's talk a little bit about design scaling. Now, the numbers, the absolute dollar numbers on the top of this, we could argue about. Frankly, if I take and do some sort of estimate on the amount of tape outs that occur per year and do any kind of matrix multiplication of tape out per node against this, I quickly run out of money in the industry. And I know we as a company are currently doing a 7 nanometer chip, and I've seen the cost, and it's not to this $200 million level. But whether the numbers are exactly correct for any particular chip, the trend line is mapped well. And that is that it becomes increasingly more expensive to do design as we move down these technology nodes. Design cost does not double, and so on a design cost per transistor basis, it continues to be cheaper, but eventually this becomes a problem in terms of NRE when you're looking at what the end market might be, and can act as a damper in terms of being able to do the amount of chips that we'll need to do to take advantage of the opportunities we've already discussed. Now here, look back to know which way to look forward. The history of the EDA industry has been about increasing layers of abstraction. When I joined the semiconductor industry back in the 80s, there was an awful lot of work still being done at the transistor and SPICE level. In the early 80s, that transition to gate level, driven a lot around things like ASICs, occurred. In the late 80s, early 90s was a transition to RTL to, again, enable us to design more at a quicker level. And we've been talking for a number of years now about moving that abstraction one level up to be taking it to the C or systems level. And we're seeing some very encouraging trends at this point in time that that's actually happening now. Now, it's mostly being driven around the fact that this is an almost ideal application environment, application level to do things like AI accelerators, video codecs, that data processing you're looking to do on the edge. And it's not just because of the ability to be more productive, although that's certainly true. You can see here a quote from Bill Daley at Hot Chips in August of 19 that talked about the level of people it took to do the design of that particular chip. But I think probably even more importantly is this concept of being able to do software-like velocity. What does that mean? Well, it means that you can do architectural exploration in a way that is difficult in RTL. By focusing on the algorithm and allowing the tool flow to give automatic implementation, you're able to target a power performance area spec that would be unrealizable through simple optimization at the RTL level. And this is why we're seeing an explosion in usage of these tools and an expansion of capability to where our vision is being able to do not just the data path, but be able to handle whole chips in these environments, giving you the ability to not just be more effective in the implementation path, but also being able to do significantly more systems validation up front before having committed to a particular specification. Finally, let's talk about this system scaling aspect here. In many ways, the idea here is simple. Verification to us was about you had a specification for your chip and that you needed to put a test bench in place that ensured that you met the specification. Validation is about you want to make sure you verify the chip, but what you're trying to validate is what is its performance against the real-world application stack that's occurring on it. In other words, can I make sure that once I have this chip, I've booted Android, I've started to run applications, I can then monitor power to ensure that when this cell phone is built, I don't end up draining batteries more quickly than they're intended to because I didn't understand a corner case of how the chip was going to operate because of the application that was running. And then this digital twin bringing in that concept that increasingly as we look at these systems of sensors, IoT, 5G, data center, that we understand how these systems are going to be operating in the real world in the complexity not just of their application, but how they're pulling in data from the world and how they're influencing what is happening in the world. So one of the clearest examples we have of that to date is a program we announced a few years ago. It's called Pave 360. And here the idea is both simple and revolutionary. So in the center is compute and analyze. That is that area where we pull together systems including hardware-assisted verification, simulation, virtual prototypes of compute applications, all of which enable us to run application stacks at a reasonable performance level to where we can validate those systems so that we can run a real-world application on top of the box and look to ensure that all the performance characteristics and functionality are met. But now what we also do is then expand that out to where in this example, since we're talking about automotive, Pave 360 is meant to validate autonomous vehicle environments. We have a sensing environment where what we can do is model scenarios of real-world data to where you can put traffic lights, traffic lanes, pedestrians, other vehicles, all in place that allow you to run these various scenarios and then produce sensor data, virtualized, that can be fed into that compute and analysis function. In turn, once that has been processed, it can then be hooked into a model of, for example, the powertrain of the vehicle, the chassis of the vehicle, a model of the human in the environment, and you can actually watch in this environment as a pedestrian crosses the road, how much braking force is being applied by the compute system, and how that's affecting the vehicle dynamics and how the person will be reacting inside the car. And we can watch all those characteristics without ever having put anything on the road or built a single chip. This is a revolutionary way of looking at how you do that trip from that verification of a simple specification to validating your performance environment, and it's critical for implementing these types of systems. And we expect this type of approach to become important across multiple environments. Things like being able to monitor, for example, in a noisy factory environment, what does that do to your overall 5G channel fidelity, and how does that affect overall communications in an industrial IoT application? And finally, going off to that vision and maybe taking it a little bit further is taking it to where the EDA environment not only helps aid in the design and manufacturing test, but also becomes an intimate part of the overall silicon life cycle. So we're ranging from things that we're doing today, for example, leveraging the ATBG structures that have been put onto the device to do manufacturing tests, to do in-system tests to ensure that a chip is still reliable, for example, in critical safety-centric applications, to being able to put in place analytics on the chip that will allow us to measure, validate, and pull back data around things like reliability, aging over time, monitoring for things like security intrusions, and helping again to further the aspects of ensuring functional safety over time. So in general, I don't think I could look forward to a decade more than I look forward to this next decade. We are increasingly a critical part of not only the electronics industry, but the overall global economy as a whole. Increasingly, we see a market available to us that should encourage investment, new design activity in the market. And we believe that as an EDA industry, we have a compelling vision underneath of this to help support that and become enablers of your success over time. So I want to thank you for spending this time with us today, and I look forward to seeing you sometime in the near future where I can get your thoughts on how you think things are going to be moving forward as we go into this next decade. Thank you very much.